Bugs! You may love them, you may fear them. No matter your opinion, they're a crucial part of our ecosystem and even to engineering as well. Insects have often been the target of biomimicry, which is when technology takes after nature to solve human problems. Currently, the leafhopper is emerging as a new inspiration. True to their name, they are often found sucking the sap of leaves. In 1952, Tulloch and Shapiro found macroscopic white powders on these inconspicuous insects, soon realized as a chemical marvel, Brochosomes. How they're made is still quite unknown, though it all begins in the Malpighian tubes, like kidneys for bugs. The tubules normally process fluids and excrete waste, but can be specialized between insect species as well. In leafhoppers, there are 4 inflated modified segments, which release brochosomes to the hind. Once released, they may go through some acrobatics to spread around their body, but it's worth it. Why? Scientists aren't entirely sure, but they do have some ideas. When leafhoppers anoint themselves, the dried coat becomes super hydrophobic, while typical water-repellent insects are simply hydrophobic with their basic waxes. What's the difference? A hydrophobic surface will induce an angle of at least 90 degrees when water contacts it, while a super hydrophobic surface will induce an angle of over 150 degrees. With this, leafhoppers won't drown in their own food or honeydew secretions. This phenomenon is caused by a rough surface the layer of dried brochosomes leave. They are hollow, soccer ball-shaped molecules made of proteins and lipids, and about 200 times less than the width of a human hair. This structure disrupts the surface and creates pockets of air, causing droplets to stay near perfect spheres and easily slide off, leading to our next perk. The coat acts as a self-cleaner, carrying away dirt, microbes, and fungi as the water slides off. Initial infection is also prevented because the coat keeps them dry, while bacteria and molds prefer damp environments. If you've ever left out food for a while, you've personally experienced this preference. Furthermore, brochosomes can be a form of camouflage, which isn't obvious if you've seen some leafhoppers. However, instead of blending in, they manipulate light. These nanoparticles allow for high UV absorption and scattering of visible light as an anti-reflective shield. Many predators rely on UV vision to spot their prey, so leafhoppers are hiding in plain sight. You might hear light scattering and think, isn't that going to reflect more light? Well, light hits objects moving in straight beams and hits our eyes in much the same way when reflected back. When hitting the surface of brochosomes, the size of the openings and hollow interior cause photons to bounce around in a process called me-scattering. When light scatters, we perceive much less brightness. Also, this process is omnidirectional, meaning it works when light hits it from almost any direction. Leafhoppers thrive because they listen to their mom and put on their coats. What can we do with this? That's where biomimicry comes in. When it comes to making these synthetically, the geometry is so practical that changing the material doesn't really reduce the effectiveness. In fact, when using some materials, it's actually enhanced. The cause, surface-enhanced Raymond scattering, is an entire topic of its own, but what you need to know is that this allows for more precise manipulation by scientists. So, super hydrophobicity is perfect for protecting clothing, electronics, and building materials from spills and weather. The antimicrobial properties are great for sterile spaces. As for light, sensors, cameras, and camouflage materials are currently being looked into. On a larger scale, clean energy could be revolutionized with better solar panels and photocatalysts. Invention has far more potential with further experimentation, all stemming from the ingenuity of a little bug right outside your door.